Okay, so today's lesson is on factorials. So this is really just about organized counting. It's really about the fundamental counting principle. So there's no like this idea of factorial, which you're going to see many times in the future, both here in this class and in lots of other situations. What we're going to see is that a factorial is just a different way of representing the fundamental accounting principle. It's a really quick way of using certain attributes on our calculator in order to figure out and calculate the number of ways of arranging objects. So as you can read from here, it says many probability calculations involve the product of a series of consecutive integers. The factorial notation is commonly used to write complex expressions more simply. Okay, so what does this mean? You can see this fancy formula below you right here, and from that you'll notice that although it looks a little bit strange, we'll be able to figure out exactly what this is shortly. Okay, so imagine a photographer, and the photographer shows up and says, I want to take a photo, and there's only two people there. How many different possible arrangements are there for those two people to stand side by side, let's say? Well, the fundamental counting principle says simply there are two people, and you have two options for the first position. One of them's used. So there's two possible ways of arranging those people. You're like, okay, that's fine. One person can be on the left, one on the right, and they switch. Two possible ways. How about three? So we do this. 3 times 2 times 1, which is 3 times 2 is 6, times 1 is 6. 6, okay, not too bad. 8 people. So let's say 8 of your friends get together and they say, let's just line up, take a picture, and let's keep doing this every 10 seconds and figure out how many different ways we can arrange ourselves from left to right, let's say. How many different possible arrangements are there that are completely unique? Well, in this case, for 8 people, it's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now you start putting this in your calculator, and you realize that 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 40,320 different arrangements. That is a massive number. 8 of your friends doing this, every 10 seconds trying to arrange yourselves, forget it. 40,320 different arrangements. That's a lot. 45. Oh my gosh. You start to think, how am I going to write this out? I'm going to go 45 times 44 times 43 times, oh my gosh, times 2 times 1. This is a huge number. If 45 people got together and said, let's line up in a row, take a picture, there are 45 factorial ways of doing this. And I just used the word factorial, and factorial says, let's find a way of writing this so that we don't have, or putting in our calculator as well, so that we realize that this unique possibility shows up many, many times where you drop consecutive integers, 45, 44, 43, 42, all the way down to 1. In this case, the number is 1.19622, I won't keep going with the decimals, times 10 to the 56 possibilities. That is a vast number. You would be very unlikely that you would ever find every possible arrangement. In fact, you wouldn't find every possible arrangement of people if there were 45 of them. Okay, so how did I figure that number so quickly without multiplying all these together? I used a calculator, and the calculator has a special function. They called it the factorial notation. So if you have some natural number, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth, you can write it as factorial. So n factorial. So you take the first number, so if it was 45, it's 45. 45 subtract 1 is 44. 45 subtract 2 is 43. 45 subtract 3, 42. And it goes on to 3, 2, 1. I could have left this as 3 times 2 times 1. Up here I just went times 2 times 1. Okay. this is read as n factorial. It's a number of ways of arranging objects where order matters. Because in this case, the order or the arrangement of these 45 people, or these 8 people, or these 3 people, it matters. Whether the exact position of each of them in that row is very deterministic, and it's required that you know that order, and the factorial is a way of discovering that. So in the example above, the number of arrangements of 45 people, if you take all 45 of them, is 41 factorial. So it turns out that on your calculator there is a button that does the factorial for us. So not sure you can be able to see this, but 5 factorial on your calculator. I'll put this down here. You might be able to see it here. Okay, so on my calculator, some of you have to use this probability function if you have a not so good calculator. You go 5 shift, and there's the little factorial button there. You've probably seen it on your calculator before, but there's mine. I press it, 120. So 5 factorial is 120. And again, that was 5 times 4 times 3 times 2 times 1, like so. Okay. 45 factorial. That is that number I showed up above, 1.19622 times 10 to the 56. Huge number. All right, 69 factorial, 1.711 times 10 to the 98. Huge number. Okay, 70 factorial gives me an error. Now, depending on your calculator, it may or may not give you an error. Most calculators won't go over 10 to the 98. If you're using your phone, I think it actually will go over. So 7 factorial is computable in your calculator, or depending on the type of calculator you have. Once you get over 10 to the 98, once you get over 10 to the 100, you get an error on your calculator. So that's just important to note. Computers can obviously go further than this. Some phones actually can go further than this, so you don't, it's just a limit of most calculators. But the numbers are vast. They are hugely vast in terms of size. All right, so how can we evaluate these? Well, just to show you some different ways of doing things, we can expand things out to simplify. So if I give you the 11 factorial over 4 factorial, you could type in 11 factorial divided by 4 factorial and get the answer. But what I wanted to show you is that you could also write this out like this: 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. I don't need to write 4 times 3 times 2 times 1 because I know that this is being divided by 4 times 3 times 2 times 1, which is 4 factorial. You may want to pause that, rewind it just to see that. They divide out. So 11 factorial divided by 4 factorial, it's 11 times 10 times 9 times 8 times 7 times 6 times 5, which is 1663200. 1,663,200. Okay. What's 90 factorial divided by 80 factorial? Well, 90 factorial is larger than 70, so you get an error. So we can't calculate this on most calculators. Remember that. This is on most calculators. But we could evaluate it still by going 90 times 89 times 88. Oh, I can actually just write factorial because it'd be 87. I don't want to write them all out. Look at that. That's 88 times 87 times 86. It's what would trail after that. Divide them out. So it turns out that this, although you can't do it in your calculator, is 90 times 89, which is simply 8,010. Okay, some slightly more academic and theoretical stuff that we can do here is how can we rewrite n plus 2 factorial? Well, since n factorial is just a reduction by 1 of each case, n plus 2 factorial would be n plus 2 times, then we drop it by 1, n plus 1, n minus 1 times dot 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 times 3 times 2 times 1, like so. Just drops continually by 1. What does n minus 1 factorial look like? Well, the first term is n minus 1. Then we drop it by 1. Drop by another 1. And this continues down. Okay. So what we're going to look at now is a permutation. Okay. Well, what is a permutation? We're starting to learn some new terminology here. We talked about the fundamental counting principle, and now we've talked about the factorial, which is a way of representing the fundamental counting principle when you're not replacing items or when you're arranging distinct items. So now we run into this term called a permutation, and it's a very common term you'll hear around a lot. A permutation of n distinct different objects is an arrangement of all the objects in a definite order. The total number of permutations or arrangements is denoted by, there's two ways of writing it. You'll often see it as p, n comma n, or npn. This is the way usually it shows up on your calculator. This is simple. Sometimes it shows up this way. And it turns out that since we're talking about, let's say we have 8 objects, how many permutations of those objects are there? Meaning, if we have 8 of them, and I want to take all 8 of them and arrange them in some specific order, there would be 8 factorial ways of doing that. 40,320 if you recall from the previous page. So how we write that is that by definition, a permutation of n objects taken n at a time is just simply n factorial. It's going to take a few minutes for this to settle in and see some examples as to what's really happening here. Let's say that there's a choir, just picking some examples here, and they've learned 8 songs for a spring concert. In how many ways can the director arrange these songs? So you're like, okay, how many different ways can they, sing the songs? There are 8 songs, and we want to arrange them in 8, like we want to take 8 of them at a time and find out how many arrangements there are. So 8 objects taken 8 at a time, where the order matters, says that there would be 8 factorial, which is 40,320 different arrangements. It says this could also be done using the fundamental counting principle. Of course it could. We could say that there were 8 songs to pick from for the first one. There were 7 for the next one. 6, 5, 4, 3, 2, 1, which if you multiply it in your calculator, gives you the exact same thing. So what this tells us is that, we can't repeat songs in this case. And that's an important part about permutations. They're distinct objects, we're taking them, and once we've taken them, they're gone, so we have to drop by 1 each time. That gives us 40,320. Okay. That's a lot of different ways that you could run that concert. Now, step forward a little bit. Permutation of n distinct objects taken r at a time. And now you're thinking, what do you mean n distinct objects taken r at a time? Let's say that we had 8 songs, but we didn't want to arrange them in 8 different ways, or sorry, not 8 different ways, but we didn't want to play all 8 of them. We only wanted to play 5 of them. How many different ways could we arrange 8 songs where we're only going to take 5 of them at a time? That's what a permutation is, where we have n objects taken r at a time. And so where the order matters. And it's, it's super important that you at this point realize that for a permutation up here, order matters. Okay, so permutation of n distinct objects taken r at a time is an arrangement of r of the n objects in a definite order. The total number of such arrangements is denoted as this: p n of r, npr, like so. Okay, so using the fundamental counting principle, what we see is that, now there's a big derivation for this that I could show you, but I'll spare you that for now, is to show you that if you have 8 objects and you're taking r of them at a time, it's npr, which is n factorial divided by n minus r factorial. Now, to go back to the other problem where we had 8 songs and we wanted to take them 8 at a time, so that is play all 8 songs. How many ways can we do that? If you recall, it was 8 and 8. So it was 8 songs taken 8 at a time, which is n, or 8p8, and 8 factorial over 8 minus 8, or 0 factorial, is just n factorial. And so now you're thinking, what? What are you talking about 0 factorial? 0 is not a thing, or 0 factorial, what does that even mean? And how can you take n and divide it by 0? And so that's another thing that we're going to have to worry about in just a few minutes, or at least discuss. Okay, so we'll do that in just 1 minute. Okay, let's say that you have an investment club, I don't know, and there's 5 members, and you want to select a president and a vice president. We've already done this problem before. There's 5 people. I want to select a president. I have 5 people to pick from. Once I've picked a person to be president, there's only 4 people left. So there are 20 ways to pick a president and a vice president. They're distinct objects, so that's why it matters. The order matters. That's why we're dropping. So there's 20 different ways of taking 5 people and arranging them into president, vice president situations. Okay, there's another way to think about this. The other way to think about it is say, how many groups of 2 people can I make from 5 people that are distinct? Meaning that there'll be a president and a vice president in each case. Well, what we do is we write it like this. We say, how many permutations of 5 objects taken 2 at a time are there? Okay, so the fundamental counting principle said this, and so we write 5p2, so you can write it as the permutations of 5, 2, or 5 objects arranging or picking 2 at a time. And we use our formula up here, and we say, well, that's 5 factorial over 5 minus 2 factorial, which is, and that's just 5 times 4 times 3 factorial, which is 20, the same answer. So, there's a lot happening here, and you can see that you get to the same solution of 20. You could also put this in your calculator, right? I have my calculator here, and you write 5. My button is right there. You can see this. Maybe I'll do that. NPR. So I do 5p2 is 20. So it tells me if I take 5 objects and I want to arrange them, or take groups of 2 of them, how many different arrangements are there? There are 20. Okay. So if we go back to our other problem before this, and let me just double check that it's not on this next page. Okay. So actually, let me just double check. Yeah. So we'll see this in just another minute, but another way of thinking about this is that, we've got these 5 objects and we just want to take 2 of them at a time so we can get this 20. Now, if we look at a situation as well, let's say that we had those 8 songs going back. And so arrange 8 objects, which means if we want to arrange 8 different objects like we talked about before, we said there's 8 objects, take 8 of them at a time. How many different arrangements are there? That's 8p8, which is 8 factorial over 8 minus 8 factorial. Like that. And you think, you can't divide by 0. But we know that pnn or npn, if these two numbers are the same, we realize that it was just 8 factorial. Okay? That means that 0 factorial, by definition, must equal 1. So it's a little different than a regular 0, because typically you can't divide by 0. But 0 factorial is 1. Now what does this mean? If you have no objects, how many ways can you arrange them? The answer is 1. And that is no way. So again, the way to think about 0 factorial is to say, if you have 0 objects, how many ways can you arrange them? There's only one way to arrange 0 objects, and that's to not arrange them. So that's a sort of a way to think about what 0 factorial is. All right, let's take a quick look at a sample problem, and then you're going to start your work on this. Okay, so let's say, now I'll write up here what the formula is so we can have a look at it. Okay, the number of permutations, where order, remember permutations is that order matters. Okay, again, it's related to the fundamental counting principle, it's related to factorials, so don't get overexcited about what's happening and what's all this new terminology. You just have to learn that terminology. Okay, so this next thing says there are 15 players on a school baseball team. Sure, great. How many ways can the coach complete the 9-person batting order? Okay, show 2 different ways. Well, one way is to say, all right, first person up, there's 15 people to pick from. They can't bat again. 14 times 13 times 12 times 11 times 10. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 different ways of arranging the batting order if there's a 9-person batting order. Okay, so you're thinking to yourself, there's got to be an easier way to do this, and the answer is very large, and we'll figure out the answer on the next slide, sorry, and we'll just write it in there. Okay, so another way of doing this is say, how many arrangements of 15 people are there if we're going to take them 9 at a time? I'm writing it all up for your work. That's 15 factorial. And if I go so it's 15 factorial over 6 factorial. Now, if you're clever and you're looking at this, you'll realize that if I expand 15 factorial, it becomes 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 factorial. Oh, well, 6 factorial over 6 factorial divides out. So this term here is exactly the same as writing out the fundamental counting principle for 15 objects and you're only taking 9 of them. Makes sense. Now in your calculator, you could put in 15 factorial divided by 6 factorial, and you will get 181621440, 1,816,214,400 different batting orders. That's a lot. So you could expand it out this way to get the answer, or you could go right at the beginning and go 15 P9. Exact same answer. Writing it out like this is helpful. Using the calculator also makes it a little bit easier. Okay. Let's say that you have 10 books and you want to arrange them on the shelf. Okay. Well, if there's 10 books, I want to arrange all 10 of them. How many ways of doing that? Well, 10 factorial. We know that 0 factorial is 1. So there are 10 factorial ways of doing this. $3,628,800 different ways of arranging these 10 books on the shelf. Okay, so that's fine. Another way, I could have just done 10 P10. I get the same number as doing 10 factorial. Okay, I think you can see that. Now, assume that 3 of the books from the question above are by the same author and must be kept together on the shelf. How many arrangements are there with this condition? And you're like, okay, there's 3 books from the same author, they must be together. Well, here's the key. Put them together. 3 of the books must be together. So we'll put them together. 3 of them are used up as one entity, so these are like the 3 books. Okay, so these are the 3 books together. So if there's 3 books together and there were 10 books in total, that means that there's 8 books really. So you could put all 3 books first, or you could put one of the 7 other books there. So it means there's 8 options for the first position. You could either put all 3 books. Okay, so you can put all 3 books there, or you can put one of the other 7 books. And assume that the 3 books must be kept together times 7 times 6 times 5 times 4 times 3 times 2 times 1. Like that. Now, if those 3 books are together, what you must do at this point is realize that if all those 3 books are together, so we're not just doing 10 times 9 times 8 all the way down. If the 3 books are kept together, there are 3 factorial ways of arranging those books as well. Because if you think about it, the 3 books could be arranged in 3 factorial different ways, 3 times 2 times 1. So for every position that they hold, there are also an additional 6 ways of arranging them. So if the 3 books were here first, so I could stick the first book. Let's stick the 3 books here. Okay. So we say there's 3 books here. We'll put them in the first position. That means if all 3 books are here, so that should be a 1, then that means that there's 7 books left. 6, 5, 4, 3, 2, 1. Okay. But we know that there are 3 factorial ways of arranging those books here. And that's fine. If the book's here, then there's 7 options for the first one, times 1, times 6, times 5, times 4, times 3, with 3 factorial ways of arranging those books. So the solution becomes, if you think about it this way, it's 1 times 7 factorial times 3 factorial. Which is 30,240 different ways of arranging those books. So again, I put all 3 books first, and then I realized that there are 3 different ways of arranging these books. And in fact, I think there's one thing missing here, which is that this is if those books are first. And there's 3 factorial ways of arranging those books. There's also, the books could be here, 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 or here. 1, 2, 3, 4, 5, 6, 7. So there's actually 8 different arrangements of those as well, because those 3 books could be here, here, here. So really, we have to multiply this by 8. Okay. 0 factorial it talks about. Expand p n of n. Which we've just previously did. N minus n factorial, which implies that 0 factorial must equal 1 by definition. And we've already seen that before, because we said before that this must be n factorial. Okay, let's go one step further and take a look at this for the next problem, which is how many permutations of the letters of the word diploma are there when there's no restrictions? No letters are repeating, which is important for this. So if there's no restrictions, there are 1, 2, 3, 4, 5, 6, 7. If we have 7 letters, and we're going to take them 7 at a time, which we know is 7 factorial over 0 factorial, which is just 7 factorial. So you can put it in your calculator as 7p7 or 7 factorial, and you get 5040. Let's stick L in the middle. So there's 7, so there's 1, 2, 3, 4, 5, 6, 7. The middle's here, that's got to be L. Okay, so if that's L, it's really just a 1. There's only 6 times 5 times 4 times 1 times 3 times 2 times 1. So we use the fundamental counting principle to figure this out. Since this is the L, it must be there. This is a 1, so that's where the L is. And there's only one way of having that there. Then the answer becomes, if we write it out, it really is 1 times 6 factorial. There's only 720 arrangements where L is in the middle. Well, let's say that the O and the I have to be together. So stick them together. So if the O and the I are together, then what we can actually look at is we can say to ourselves that, and this is where this goes back up to this question here where I made it a little more complicated, I think, than I had to. There's 7 options, but since they're together now, I realize that if I put the O and the I together, then I'm left with 1, 2, 3, 4, 5 arrangements. So the O and the I are together, which is 1, then there's 5 other letters, so that's 6 times 5. And since they're together, there's only 6 times 5. Wait, is that correct? Hang on a second. Yeah, think this through. So O and I together, there's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. So there's 5, right? So if we have 5 options, and there are, that's right, I had to go back up to here for the 7. So it was 6. So there's 6 options. You have the O and the I together, or any of those other 5 things. So it would be 6 times 4 times 3 times 2 times 1, like so. Now, because the O and the I are together, we have to multiply this by 2 factorial, because there's, for each of those arrangements, there's 2 different ways of arranging those, the O and the I. So it's 6 factorial times 2 factorial, which is 1,440 different arrangements of that. Okay, how about the O and the I are not together? Well, just take the total number of arrangements, subtract when they are together. The total number of ways of arranging these 7 letters is 5040. Subtract when they are together. So there's 3,600 different ways of arranging it where O and I are together. So again, these types of problems get a little tricky when you start thinking through them. As you can see here, when I was thinking about, if the O and the I are together, then there's really only 6 objects left. Okay, there's the 1, 2, 3, 4, 5, and then the 6th object is those 2 together. So how can you arrange 6 objects? Well, you can arrange them in 6 times 5 times 4 times 3 times 2 times 1 ways, or 6 factorial. Then you realize that you could have O and I and O for every single one of those possibilities. So you multiply it by 2 factorial, and that's why you get this. Same thing up here. I had started by saying put the 3 books together, and I was actually correct at the beginning to say 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 multiplied by 3 factorial, which is exactly what I ended up talking you through, where I said put the book first, and then there's only 7 other books to pick from, 6, 5, 4, 3, 2, 1, and then flip these around in 6 different ways, right? But then there's 8 positions left, 1, 2, 3, 4, 5, 6, 7, 8 positions left that I had to multiply it by. So had I done it the exact way I did the one down here, I would have written 8 factorial times 3 factorial, which would be exactly that same number. So again, you can approach it from different ways to get the similar solutions. It's really about how you see it, but realizing that permutations or where order matters. Okay, from here we're going to work on the problems that are related to this.